All right, guys, so let's get started for today's workshop. A lot of you have seen me from our previous workshops on Code Hiraku. My name is Mihir Thakkar. I am the founder and instructor at Code Hiraku. And thanks again for joining today, especially because it's a weekday. We generally host our workshops on weekends, but I decided that no, it was time that we start doing a lot more of our live sessions. So thank you for joining in after a tiring day at your college or your work. To give you a background on what we do, we host live and interactive sessions like these so that students like you can be present in a live class with your instructor and ask questions in real time rather than watching a pre-recorded YouTube video and asking your questions on some kind of forum. So the whole point of these online live sessions is to make this session as interactive as possible. So please do ask me your questions on the chat box. I'll be more than happy to answer your questions. If there is something that I'm not aware of, because I can't know everything, I'll refer you to some external resource or no, we'll get back to you after the workshop. So having said that, let's get started into our workshop. We have a lot of things to cover today, and I hope you all are excited as much as I am. So let's get started. So let's see what we are going to do today. I'm going to go over some of our previous material so that everyone is on the same page. And then we, as you know, this workshop is called Using Gradient Descent for Machine Learning, but why the hell do we need it, right? So I'm going to go over what is gradient descent and know why do we need it in the first place. We'll also revise some basic math concepts because no, I don't want this to be just a black box for you. You put in use some scikit-learn functions and you don't know what's happening behind, you don't know the math behind it. So I don't want you to be those kind of machine learning engineers or who don't know what's actually going behind the scenes. So we'll do revise some maths and nothing over here is something which you haven't already studied or you haven't done in your high school class before. Everything you already know it, you just need to be reminded of those things. Okay, so especially if you're doing engineering, we have derived even worse equations. So this is very easy, don't worry about it, we'll just go through it together. And finally, we just don't want to talk theory. The whole point on any course or any workshop at Code Hiraku is to be able to build something by yourself. We'll be implementing gradient descent in Python, and hopefully you will be able to share it with your friends on social media and show them how such a cool thing that you have made today. Okay. If there are any questions, please stop me at that point and I'll be more than happy to answer your questions in the chat. All right, so let's get in. Let's do some revision. You are given a function, let's say y is equals to x. So we have this basic function. You have seen this a lot of times. So y is equal to x is an input function, and you apply it to a transform. Let's say you give it to a function f of x which is equals to x squared. There is a box over there which transforms this input to, which has a transfer function of, let's say f of x is x squared. So I want you guys, if you have a pen and a paper, just draw what the output of this box would look like. All right, so this is what it looks like. Pretty basic. Given y is equals to x, if you apply it to a box which has a function f of x is x squared, you will transform it, you will transform the input and you'll get something like this as an output of this from this system, right? So pretty basic. You have drawn these kind of graphs in your engineering school or in your high school as well. So how is machine learning related to this, and why am I showing this to you? So what happens in machine learning is not very different. When you're doing machine learning, you are given the input. Again, it's the same input like we saw before, and you are given a desired output. Okay. Before this, we were given the input function and we were told calculate the output of this function. But now when you're doing machine learning, you are given the output function as well. And your job as a machine learning engineer is to find this function which would result in this kind of transform. Okay, does that make sense? Before, now we are used to doing this. Someone has given you input and a function, and they tell you calculate the output of this function. So you say, okay, f of x is x squared. You draw, for all x's you plot y, so you get something like this. And now what you are trying to do with machine learning is you are trying to learn this function. You look at the input, you look at the output, and looking at both of these things, you try to learn this function f of x, which could result in this kind of output. Okay, so this was like very high level overview of what machine learning is at its core. When you ask someone what machine learning is, they are going to tell you something trying to teach computer how to learn, or no, something on that lines, like Wikipedia definition. But when it comes to its essence, this is what any machine learning algorithm is trying to do. It's trying to learn transfer function or transform, which would result in the desired output. Okay, any questions on this one? So let's revisit some more maths over here. Let's say you're given this graph and this line over here. A line will have an infinite set of points, but to really represent it, you don't need that much of memory to store this line, to represent this line. So how, okay, forget about in a computer's memory. How would you represent this line mathematically? Yeah, Suchit got it right. Using y is mx plus c, or sometimes you call it as mx plus b, right? So y is mx plus b. If you can represent these two parameters, or these two variables m and b, you know what that line is going to look like, right? And where m is the slope of this line, and b is the point where it cuts the y-axis, or where it intercepts the y-axis. That's why it's called the y-intercept. So can someone, just by looking at this line, tell me what the equation of this line is? So let me give you a hint. Okay, the slope of this line, the slope is the amount by which the line is rising on the y-axis for every point that you go towards right. So over here, let me get my pointer. What is the amount by which the line is rising on y-axis if you move one block towards the right? So what is the slope of this line? 0.5 units, right? So you went up by 0.5 units. So the slope of this line is 0.5, right? So m is 0.5 and b is 1. It's right in front of us. The point at which it cuts the y-axis, b is 1. Okay, so equation of this line is y is 0.5x plus 1. Now you might be thinking, why on earth is Mihir talking about equations of line in a gradient descent class? Well, the thing is, these m and b, these two things are gonna be heroes of our class today. You guys know all of this. I'm just trying to revise some of these things again. And how is this thing related, anywhere related to machine learning? There are two main types of problems in machine learning. The first one is called regression problems, and the second one is called classification problem. So in a regression problem, you are given, let's say over here is an example of a regression problem, wherein you are given on the x-axis over here, you are given the number of hours that a student studies. So over here, it's like 2 hours, 4 hours, 6, 8, 10, and 12. Okay, and on the y-axis is the amount, the score which he will get on his exam. So if he studies more hours, he should get more scores, right? So someone has given this data set to us and told us that now, given this data set, can you create a model, machine learning model, which will predict, given the number of hours, how much the score of that student is going to be. Forget machine learning, forget, you don't know anything about machine learning. Put everything aside. Even if you know machine learning, forget about it. Let's say someone gave you this data set and then told you that a new student has come to us and he studies about 10 hours. Okay, so what is the most likely his score on the exam going to be? Now this has to do nothing with machine learning. It's pure data analytics, or no, just seeing the data in front of you and making sense out of it. So Suman says around 45-ish. Someone said about 50 to 60. So what all of you are doing in your head is, you are creating a model, in your head of this world. Okay. And this is what we are trying to teach our computers to do as well. So you are creating a model in your head. And for linear regression algorithm, what we try to think of all our problems is, we try to oversimplify it. We think that everything in this world has a linear relationship. Over here, there is definitely some linear relationship. But if you are applying a linear regression algorithm, what we say is we oversimplify the problem and say that, you know what, these two parameters have linear relationship between them. Okay. So we draw this line, which we call the regression line. Okay. And this is what you essentially did in your head as well, right? You drew this imaginary line in your head and said that given this point over here, what is the expected result now? Now, because it is more clear now, can someone again comment on the chat what's the expected output? Or no, what will be our prediction for the number of hours as studied as 10? Around 55-60, right? So this is our prediction. No, it's around 60, and this is what our machine learning model is going to predict as well. It will draw a line which will fit all these points in the best possible way. It will draw a line which is closest to all these points. And once you have this line, if you give any other point on this line, it becomes very easy for me to tell you what my prediction is going to be, right? It's just a matter of, let's say someone gave you this point. So what you're going to say is, okay, for 10 hours of study, I can get y is equal to mx plus b, and I can get the output as my prediction. Okay. So again, I'm going to ask the same question again. I want to make sure that everyone gets this point. How many floating point numbers will you need to represent this line in computer's memory? Again, a question for you guys. How many floating point numbers, or how many variables do you need to represent this regression line in a computer's memory? And this equation of this line is right in front of you. Okay. This is the line. I want to represent it in computer's memory. And this is the equation of this line. Guys, the right answer is 2. We need only 2 variables to store, one to store m and the other to b, right? The y's and the x's, you don't, like, these are infinite set of points. You don't need to even store them, right? This line, if you know the m and the b, you can draw a line. Okay. So you need only these 2 parameters to represent a line. So once you understand that, so you had predicted 60 over here, right? And someone tells you, you know what, the student actually went to the class and he scored more than 60. It's like around 85, 90. That's what he scored. So what is our error going to be in this case? The error is nothing but the difference between our predicted value, which was 60, and the actual value, which is like around 85, 90. So error of about 25, 30 points, right? So this is what the error in our regression model is. It's simply the difference between what we predicted and what the actual result was. Okay. So let's see if you are with me on this. A quiz for you again. Calculate the total error, mean error, and the mean square error for the following set of predicted and actual results. Go ahead, take your pen and paper and do these simple math calculations. There is no rocket science in this. I want you to find what the total error is, the mean error is, and the mean squared error. Just by the names, you don't even have to remember the formulas for these things. Okay. If you understand this thing over here, for 1 point, the error was the predicted value minus the actual value, right? And similarly, you are given, you made 4 predictions and you have 4 actual values. So what is the total error, mean error, and the mean squared error? And you don't, again, just look at the name of these terms. You don't have to refer, don't Google, don't try to Google for the formulas of these things. All right, so let me show you for the total, and let's see if you guys want to correct your answers for the rest of the two. The total error is nothing but the difference between all of these, okay? And you just add what was the difference between all of these values, and you just add all of them up. Okay, so it's 2 plus, over here we made the correct prediction, so the error is 0. Over here we were off by 2. Over here we are off by 2 again, and over here we are off by 2 again. So 2 plus 2 plus 2 is going to give us 6. Okay, now does anyone want to correct their answers for the rest of the two? If no, if you did not get the first total error correct. And guys, are you with me? Is there any confusion? Because a lot of you have not answered the total error correctly, right? So please let me know what you were thinking. Did you no, just do 30 minus 32 and you had this as minus 2, something like that? All right, the second one. Mean error. Total error divided by number of observations that we have, right? 6 divided by 4 is going to give us 1.5. And mean squared error, you just do the same thing as you did before. But over here, you notice that over here, we had to take 32 minus 30, right? Because we were actually interested in how much we were off. And we don't want like minus 2 over here. Otherwise, we are going to think that, no, our error is less. So if we are trying to put this in a formula, it becomes difficult to see, oh, whether you are going to do actual minus predicted or predicted minus actual. So what you could do is just square all of those up. And if you square them up, what's going to happen is you're going to get absolute values. The mean squared error is going to be 3 over there. So if you guys got the same thing, what's the objective of our class today? We already seen that someone gives us this data point, and we are trying to solve regression problem using what we are calling something as gradient descent. Okay, we don't know what this gradient descent is, but I'm promising you that gradient descent is going to help us find this line over here. So what we want to do is we want to create a machine learning model, and you know that to create this line, finding the line is equal to finding M and B, right? And we want to find this line in a way that is going to give us the least error, right? You know already how to calculate error. We just did that, right? But we want to find this line in a way that we get minimum error, right? That makes sense, right? We want to find a line which is closest to all these points so that our predictions are not off, right? So we want to find this line, and this is what we are going to do today. The whole point in this class is we are going to find these two values, M and B, for a given data set using what I'm telling you is a friend of ours, which is going to help us do that, which is called as gradient descent. What we are going to do, or the basic intuition behind this gradient descent is it goes like ages back. Okay, it's not something recent. Have you guys heard of that story of the spider which is trying to climb up a cave and then falls again and tries again? So what's the moral of that story? Again, this might be funny for a machine learning class, but yeah, this is the idea behind gradient descent. Okay, the spider which is trying to climb a cave and it keeps falling, it tries again. So what's the moral of that story? If you understand that, you understand gradient descent, trust me. Srikant says, try again. Try and try till you succeed was the moral of the story. And that's what the basic idea behind gradient descent is. It's a trial and error method. Some fancy people have called it gradient descent. And again, the machine learning is full of those things where these scientists or these computer scientists have renamed all what high school kids already know, and they rename it to something which is very fancy, And again, I'm not saying that they are stupid or no, there is no logic behind it, but uh, I think that sometimes they do it too much. They take the same concepts which are taught in high school 12th class. They would rename it for their own purpose, okay, because they understand it well. And we are going to see a lot of example of those things happening. You're like, oh, I studied this in 12th class, but why is this guy calling it something else now? Like, yeah, so that you can't, so that you think that machine learning is very difficult to understand, okay, but it's not that. Stick with me and I'll show you, I'll remind you all the names that you already know and what do these fancy people call it as well, okay. We start with the random line, okay. The spider has to start somewhere, okay. So over here as well, we are going to use trial and error to find the best line. We start with the random value of m and b. So let's say we start with the random value of m and b and we get a line like this, okay. So given this line, do we know how to calculate error? Yes, we know how to calculate error. We'll take the differences of all these points. Now with respect to this line, we'll measure all the different distances. I'm only showing 2 arrows over there because I think I'm too lazy, but no, essentially you will add all these error up, and what you're going to get is the total error. Or now if you want to do it using the mean squared error, do it that way, use the mean squared error. Okay, so the next step, we know what the error is. What we're going to do is adjust m and b such that the error reduces. Makes sense, right? You over here, the error was more, okay. Now you see I have adjusted this line that it moves slightly up. So the error has reduced now. The line has tilted a little, okay. The error is less. So what's going to happen is, you got a better line now, okay. It seems like you are moving the right direction, and you just repeat this until you find the best approximation. Do your best. Sometimes you can, sometimes you can't. That's what we're going to see in gradient descent as well. It's not every time that you're going to end up with the correct answer, or no, you're going to end up with your answer is not going to always converge to the right place. So this is the basic idea. It's like trial and error. You start off with a random value of m and b. You calculate the error. You adjust m and b such that this error reduces, and that's it. You just keep doing that again. This is like common sense algorithm, and it does not only apply to machine learning, okay. It is an optimization algorithm. Again, I want to make sure that you guys don't think that gradient descent can only help you with kind of lines that we are trying to draw. So answer in the chat box which of the following statement is true. Can gradient descent be applied only to regression problems? Or gradient descent is an optimization algorithm which can be applied to any problem in general? So all of you are right. Now we all seem to be agreeing that it's just an approach to come with the values of this m and b, okay. So in any machine learning problem or anywhere, if you come across a situation where you need to find the values of a parameter which will increase your output of a function or decrease the output of a function, you could use the gradient descent algorithm in some form or the other, okay. So it's like an approach that you could use to increase or decrease the output of something, right? So let's get started building it, because there is a lot of things within this as well that and there is some math that we need to do, some derivations, but we'll come to that after we have already understood until now. Go ahead, download this, extract it in a folder, and let me know in the chat box once you are done. So from my download, I'm moving it to a folder on my desktop. I've created a folder called Code Heroku over here. Okay, I'm pasting it over here. So just create another folder somewhere that you would like to work on. and extract it. More importantly, don't forget to extract. Don't just double click. If you're using Windows, you might forget that. Just say extract. So go inside this GD folder and you should be at this point. Once you are over here, let me know in the chat box. The next thing that I want you guys to do is open your Sublime text and you open this file gradient_descent.py and go over it and see what's there inside it. Okay, so you could say right click and say open with Sublime, or you could open the Sublime text window and go to file, open, and find this file. So once you are over here, we are going to use the pandas function and we are going to use the pandas library, and I want you to Google. Okay, if you have, our basic philosophy is that we don't tell all our students what to do or which line of code to write. I want you guys to be able to figure it out by yourself. So go to Google and find which line from pandas library are you going to use, or which method from pandas library are you going to use to open the CSV file and read the CSV file. Okay, and if you have already seen our previous videos or been to our past workshops, go ahead and write that statement, use it, and get your data frame in place. So Rohan says read_CSV. Shrikant got that right as well. Read_CSV. So why don't you guys go ahead and read this data set and use the read_CSV method from pandas to read this file. Okay, so I think most of you are getting it right. So let me just go ahead and do it as well. I'm just gonna say df, which is data frame. The name of the object or the class that it returns is a data frame, and that's why I'm using df over here. I'm gonna say pd dot read_CSV, and we're gonna give a file name which is student_scores.csv. Okay, save this. So let's read this out. So let's read this. We have read the data frame. So let's just print it out and see if we are getting it correct. So save it and just build it or run this file. If you are using Sublime Text, Atom, or if you are using any, you could use any text editor which you are comfortable with. I had suggested that you use Sublime if you have seen our prerequisites, but if you are comfortable with any other text editor, that is fine as well. So just build it. So on Sublime, I would say Control+B to build this file. And first time it will take some time, but after that it will be quick. So we have printed our data frame over here, right? So we got all our values. So we have 0 to 24, which is 25 set of values. And we have the hours over here and the scores of that student in the second column over here, right? So let's just separate out these columns as well. And we also need to plot it. That's what the instruction says. We need to plot this data frame on a screen. So let's just go ahead and do that. I'm going to say X, which are all our X's, which is, we're going to say data frame of, on the X axis, we need the hours, right? So I'm going to say data frame of hours. On the Y axis, we need data frame of scores. Okay, so these were the column names. I'm just giving this over here. No rocket science in this. Pretty simple, right? So I'm just separating my X-axis and Y-axis together because I want to plot them out. Okay, and the way we are going to plot it out is we are going to say, again, go ahead and search on Google. We are going to use the library matplotlib. Okay, so we are going to use this matplotlib library. So go on Google and tell me which method are you going to use to plot this thing. Here's how I would go about looking up, right? So I'm just going to go over here and let's say I want to, Mihir has told me that you want to use matplotlib. Okay, so using matplotlib, let's even say Python, right? Because we are using Python matplotlib. And then we want to say plot, okay, let's just say plot two values, or let's say two values or two variables. What do we get? So the first thing that comes up is this guy over here. So okay, it seems like it has matplotlib.py plot, and this is what I have seen in our program before as well, right? It's the first line or somewhere on the top of first or second line of our program. And then you just say plot.plot, right? So you can give a series over here, and then you could say plot.show, which is going to give us this graph, right? Or if you have two series, you can give the first and the second as well, right? So this is what we are looking for. So there is no rocket science in that. I just Googled and I got that as the first result. So let's go ahead and use this. So we're going to say plot.plot, and I'm going to give my x's and my y's. Okay. And you could use plot.scatter over here as well. And I'll leave that up to you to find out what's the difference. But what you could do is save it and then run it. So do Control B. And we need to also say plot.show. Otherwise, it's not going to show us anything. Save it. I'm also going to comment out the print statement. We don't want unnecessary print statement. It was just for us. And build it. And we get something, right? And can someone tell me why do we get this kind of scribble on our screen? So can someone tell me why is this happening? Well, because our data is not arranged properly, right? So what it is trying to do is trying to draw unnecessary lines between our data points, right? So instead of drawing these lines, what if we plot them as individual points? And to do that, what we're gonna give over here is another parameter. So let's try this. Yep, this makes a lot more sense. And can someone remind me what our objective is? What are we trying to do over here? We are trying to draw a line which is closest to all these points, right? We are trying to draw the best fit line. And what's the name of algorithm that we are using to do that? Yeah, gradient descent, right? That's the name of our workshop. We are using gradient descent to find a line which is going to be closest to all these points. And why do we need that? Why are we interested in drawing a line which is closest to all these points? Why are we trying to draw a line, something which passes from these points over here? Yeah. So Lakshman, to predict, right? That's the correct answer. Shrikant, it's not just to reduce the error. We are trying to draw a line which has the least error, right? But why are we doing that? So that when someone gives us a new point in on x-axis, right? Tell me how much the score is for 5 years of study. You could you could go on the x-axis over there and go on the line, and just like we did before, you could plug in y is mx plus d. The m and b of that point, so you get the answer of y over there, right? So the reason why we are trying to draw a line which is closest to all these points is we want to be able to predict the values. When someone gives us a point on x-axis, we could say that because we know this line, because we know the model of this world, we can predict the values and we can get the corresponding value on y-axis as well. Okay. All right. So that's a good refresher, and I think which is essential. Otherwise, it's like when you are in a complex story, you forget where did you start with. All right. No, you otherwise I would complete the entire Ramayana and then you'll ask me who's Ram. Right? So we don't want to end up in that state. Let's move on to the next part. The next step, the second step, which is the meat of our workshop today, is to find a function, right? To define a function gradient descent such that it takes m and b and returns a better value of m and b, so such that it reduces the error, right? Because we said that we you remember the first thing that we do as step one of our algorithm is we start with a random value of m and b, right? So let's start with a random value of m and b. Let's say m is 0, b is 0. Okay, fair enough, right? You can start with any value that you want. Let's say we start with m0 and b0. Okay, let's define a function. Let's say define gradient descent. What does it take in? It takes in all the x's, all the y's, the m and the b, right? So to start with, we are starting with the random value of m and b, and it is taking in our data set. I mean, we need to look at our data set to find this line, right? We need to give our training data, or machine learning is all about learning from the data itself. So we need the x and y, and we are also giving the m and the b as input over here. And what are the m and the b? It is the slope of the line, the regression line that we are trying to draw, and b is the y-intercept of that regression line, right? All right, so everyone is with me over until here. Let me know in the chat box if there is something which is not clear. You need to stop me at that point itself, otherwise everything else will go bouncer as well. Okay, we don't want to do that. If there shouldn't be a single person in the chat room over here who is not understanding, or if there is even slightest doubt, stop me at that point. Okay, all right, so all good until here. I don't see any questions or anything over there, so seems like I'm doing a good job. We'll see. So let's say if once we have this function over here, which is gradient descent, we have started it. Now what we want to do is we want to go through all our points in our data set. So let's just say for a point in zip x comma y, we are going to zip all our x's and y's together, because that's the way you would iterate over these points in Python. I guess there could be multiple ways of doing it, but this is how I do it usually. So for a point in, I'm going to zip all my x's and y's together, so that I'm going to get a tuple of individual x and y together. And I'm going to say x is equal to point of 0. Okay, and y is equal to point of 1. So because we do a zip over here, what it is going to do is it is going to create a tuple with the 0th element as the x, because this is x over here, and y is going to be the second element of that tuple. So no rocket science, everything is good until here, right? So once you have the x and the y, and what I'm going to do is, instead of saying it as y, I'm going to say y actual over here. So why is this actual? Because this is the actual result, right? This is the truth. This is the ground reality. So this is from the data set. I'm going to call, instead of y, I'm going to say y actual. Okay. So I'm going to say, now we're going to make predictions over it, right? So I'm going to say prediction, y prediction is equal to, okay, so let me ask you, okay, what's the answer for, what's the val, what should I use over here for y prediction? What is the formula for y prediction? So again, these y is for the regression line. Okay, so the regression line that we have over here, let me, okay, and I want the value of y on this line. What is the value, what is the formula for all y's on this line? So Lakshman thinks it's y is mx plus b, mx plus b, or mx plus c. What do others think? Shrikant thinks that as well. Yeah, both of you are right. So y is mx plus b on this line. We already seen this, right? So that's the equation of that line. That's the equation of our regression line. So we know that y is mx plus b. So what we're going to say is y prediction is m times x plus b, right? Right now we don't know what the correct answer for b is, right? M and b is, but that's the equation over there for y prediction, right? So all good until here. Y prediction is mx plus b. And can someone tell me the formula, or what should I use over here? I'm going to say error is equal to, what is the error? All of you are answering somewhat similar. You're saying that it's the absolute difference between the actual and the prediction values, predicted values, right? So what we're going to see over here is, what we're going to use over here is, we're going to say y error is equal to y prediction minus y actual. The reason why we don't care about the absolute value over here is, we're going to see in the math that we are going to use this, we're going to square these things up. All right, so that's error for us. The next thing that we need to do is, remember what was the step 2 of our gradient descent algorithm. The first step is take a random m and b, draw the line, and then calculate the error, right? So we got the error. What was step 2? This is the second step, right? We need to adjust m and b such that the error reduces, right? So let's say we need to change m and b. So we need to say m is equal to m plus some value, let's say delta m, right? So this delta m, we don't know right now what this delta m is, and b is equal to b plus delta b, and we don't know what this delta m or delta b is, right? All we know is we need to change something to m and something to b to reduce the error, right? So let's try it out. Okay, we'll come to delta m and delta b again, but what needs to happen after this? We need to we are done with our algorithm, right? We just need to just say return m and b. Okay, so we just need to return this thing back to our function, whoever is calling it, because we have updated the values of m and b, and now we have the better values of m and b, which we think, right? Remember, right now we still don't know what delta m and delta b is, right? So let's say, now let's call this function and see what happens. Okay, so we're going to say m comma b, because this is what the function returns, and we're going to say gradient descent. Let's call this gradient descent function. We're going to say x comma y comma m comma b, right? So m and b right now are 0 in our main function, right? So m and b, we have started off as 0. We are just passing our data set, and we are getting the better values of m and b. Right now we don't know what this is, but seems like if you do this properly, m and b, you're gonna get a better value. And the next thing that we want to do is also plot this regression line. So we have this helper function which is given to us over here, right? Which is plot regression line, which takes in x, m and b and plots the regression line for us. And there is no rocket science in this. So if you look through it closely, you will see that it's very basic. I just didn't want you guys to spend a lot of time on it. So I'm just gonna use this function over here. I'm just gonna say plot regression line, and I'm gonna pass it x, m and b. Okay, save it. And right now we haven't defined delta m and delta b. Okay, so we are gonna get error if we try to run this. So what we could do is, let's say arbitrary, okay, just say, let's say delta m, we don't know this is the right answer, we're just checking, we are just trying something out. So I'm just gonna say delta m is 1 and delta b is 1. Okay, we changed something to m, right? So we just incremented, we just said that, okay, I think that delta m is 1. I don't know what the right answer is, right? I'm just trying to plot it out and just see if something happens. Okay, so save it and let's try to run this and see what happens. We need to comment out the previous plot statement because we are getting two plots. So I'm gonna take this plot.show from here and let's move it down. Let's do it towards the end. Okay. So plot.show needs to be here. Run this. So you got something, right? We had a random value of m and b, and we said that okay, we plugged in random value of delta m, delta b, and there is this line over here, right? Now our job is to make sure that we adjust m and b properly such that it has a best fit. So reach to this point and we will derive mathematically what that delta m and delta b needs to be so that we can plug it in our program. And once you are done, well, you are off for the day. We are done with our today's workshop after that. Yeah, it's just delta m and delta b that we need to calculate now, because right now we are using just a random value to see if our function even works. But once we are done with that, we are done with gradient descent. That's all it is. And guys, the version of gradient descent which we are implementing today, it's called stochastic gradient descent, wherein you iterate over all of these points, right, and then adjust m and b inside this loop. There are other versions of it which are called as batch gradient descent and mini batch gradient descent. But and each one of them has their own pros and cons. But the most simpler one which I thought that I could show you and for you guys to get started with was this version. So if you go online and find another version of gradient descent, it's not that I'm wrong or they are wrong. It's just that we are implementing a different flavor of gradient descent algorithm. Okay, but the math and the logic behind all of them stays the same. Let me try to zoom out a bit over here because we need more space. Okay, this is much better. For those who are done, maybe you can get a glass of water or some snacks or something like that, because next 15 minutes are going to be intense. I'm joking, it's going to be easy. So this is what we know. The mean squared error is nothing but you take the estimate minus actual, the whole square, right? And you divide it by the number of observations that you have. So in our case, let's say if we had n observations, you just sum all the estimates minus actual and you square each one of them, right? Easy, right? This is what we had studied in high school. But for some reason, when you get into machine learning, you need to know you can't use something like mean squared error, right? So if you are doing research at an esteemed university, you can't write your equations with your best paper. You start deriving with something called as mean squared error, right? So what you do is you make it more fancy. Okay, and the way you make it more fancy is you call this as something called as cost function, right? Why do you call it cost function? Yeah, there might be some reason why it is called cost function, right? But the idea behind it is the same. The reason why it is called cost function because it's essentially the cost. Each error is costing you something, right? I hope so. That's what the literal meaning is, right? So this is, you can call it in fancy terms. If someone asks you, oh, what did you learn in today's class, you can tell them that you learn something about cost function. Don't tell them about mean squared error, otherwise they're going to think that no, you did the same thing that you learned in your high school. So tell them you studied something about cost function. And then we also know that the estimate value is mx plus b, right? We just saw the value of estimate is mx plus b and the actual is y, right? So y actual, or in this case I'm calling it y of I, from our data set, the individual y point from our data set. So remember this back of your mind, that this estimate minus actual or the error is, we can substitute that to mx plus b minus yi. Okay. Or you can make this even more fancy. Okay, in your research papers, don't call it cost function. You can say something like j of omega or something like j of theta, where this theta is a function of m and b. Why is it a function of m and b? It's right over here in front of you, right? Let me get a pointer, right? This j theta or the cost function is a function of m and b over here, right? So this cost function is, I can simplify what I said, I estimate minus actual, as just saying, instead of saying this entire thing, I can just say error square, right? So all of you with me until here, right? The cost function is 1 by n and error square, right? So very simple. There is nothing fancy over here, right? And again, what we are trying to do is trying to find what delta m and delta b is. So we are starting with something what we know. Okay, we know something about the error function, and we want to adjust m and b such that the error function reduces, or no error function is, or the error is minimum. So to find the place where error is minimum, we need to know something about the error function itself or the cost function itself. And that's why I'm showing you all of these things. Okay. So if you plot this on a graph, this is nothing different than saying this y is function of x square, and you will see a parabola like this, right? You have this error over here on the x-axis and this j on the y-axis over here, right? So if this is a function of error square, this is what the graph is going to look like. Are you guys with me until here? Let me know on the chat box if there is something that you don't understand. Otherwise, no, you won't be able to be with me going ahead. Okay, so next 2 or 3 steps are critical. So I want to make sure that until here, everyone is crystal clear. Okay, so Suchit, how do we get this graph? So this j, if you put j over here on the y-axis, if you put this error on the x-axis over here, how does a graph of y is equal to x square look like? It looks like this, right? It looks like a parabola. If error is 0, j will be 0. If error is negative, j will still be positive because the negative square will be positive, right? And this is what the graph is going to look like. Right. So given this error, let's say you took a random m and b, okay, just like we did. We took m is equal to 0, b equal to 0, and then again in the loop itself, we were saying we said delta b is 1, delta m is 1. So we're taking a random value. So given a random value, we'll get a random error some point on this graph, right? We'll get some point on this graph. So now our objective is to find this delta m such that this error reduces. We know what this graph looks like, and we know that we are at this point in this graph. There is some error, right? There is some error, and we are at this point on this graph. Now, can someone tell me from whatever you have learned in your high school, okay, what is the name of the concept that is going to help us to minimize something? Okay, we want to minimize this error, and this is what the function of error looks like. What calculus tells us that? Calculus tells us that if you want to go down over here, right, what is the minimum error? Error minimum is 0. It is over here. If you want to go to this point, the first thing that we need to do is say either to increase m or decrease m, or increase b or decrease b, right? Forget about the how much value of m or how much value of b you want to increase or decrease. The first thing that you want to know is, should I increase m or decrease m, right? And what calculus tells us is what you could do is, if you want to know that how m will affect the j theta over there, what you do is draw a tangent to this line, to this point, at the point you are. Okay, can someone tell me, is the slope of the line that you are seeing right now, the blue line that you are seeing right now, is the slope positive or negative? Everyone agrees to me that the slope is positive. Sagar thinks it's negative. Sagar, it's a positive slope. Okay, anything which is rising, if you look it from this direction over here, anything which is rising is going to be a positive slope. If you have a line which is going like this, right, it's a negative slope, right? So this is a positive slope. So what derivative is going to give us insight is, if we take a slope of this line, you go in the opposite direction of that derivative. Okay, so what we are going to do is, we are going to go opposite to what that slope is. If we go in the opposite direction of that slope, we are going to eventually reach to the minima, which is 0 over here, which is what we are interested in. We want to reach to this point, which is 0 over here, right? We want the minimum error. Can we reach over there or not? That's a different question, but ideally we want to reach there, right? So let's go ahead now with that understanding that delta m is nothing but derivative of this point over here. And what's the point? What's the curve that we have? We have j theta, or no, j omega over here, which is what we are trying to reduce, right? So let's go ahead over here. We are trying to find delta m, and we are doing a partial derivative of this function j with respect to m, because this j function over here has other parameters over here as well. There is b, and the y is a constant over here. We need to find how to adjust m and how to adjust b, right? But we can't find the answers to both of them at the same point. So we are doing a partial derivative, and we are not doing a regular differentiation. So we are doing a partial derivative of this function, because we want to find the slope of that line, right? And we'll go in the opposite direction of that slope. So let's do a partial derivative of this function j with respect to m. So do we know what the value of j is? Yes, we know it, right? From here we know what j is. J is 1 by n summation error square, right? So let's plug that in over here. Okay, so can someone tell me what's the value of the partial derivative of error square? Okay, first tell me what's the value of, from our very basic calculus class, d by dx x square. What is the answer to d by dx x square? A regular differentiation. Forget about 2x, right? So what we are going to do over here is, we are going to say, we're going to do the same thing over here. We are going to use the power rule, which is d by dx x raised to n is going to give nx raised to n minus 1, which is what you guys got there. But what the chain rule tells us is, if f is a function of g and g is a function of x, okay, so f depends on g and g depends on x. And if you're trying to take a derivative of f with respect to x, what you could do is first take this derivative, which we got 2 error, and multiply this with d by dx of the third, the final thing which you are dependent on, right? So over here, as you know, that the error actually depends on m and b. So we can't just get away by doing just 2x over here. So we can't just say 2 by n times error. We also need to multiply that by the partial derivative of the error itself, which is mx plus b minus y, and we need to take it with respect to m. And the reason why we are taking it with respect to m is because we are trying to find delta m, right? And if you take partial derivative of this thing with respect to m, everything else is constant, right? So d by dx mx is going to give us just x, right? Because x is a constant. This is not usually how we do it, right? So in generally you will have x which is not a constant, but over here x is a constant, b is a constant, and y is a constant as well, right? So everything else is gone because there is m over here, which is what we are differentiating with respect to. This x gets left out. Okay, this constant still stays. Everything else becomes 0. This x will come down over here, and this is the final answer for what delta m should look like. And remember, what we are going to do is, this is the slope of that point at that the tangent, the slope of that tangent at that point, right? And we are going to go in the opposite direction of that tangent. So similarly, what we have done it over here for delta m, can you guys work out the equations for delta b? Okay, everything else is going to stay the same. Okay, don't worry that, no, how am I going to be able to do it? It's not difficult. Try to plug in the same concepts. The only step that is going to change is this step over here. Okay, this step, the answer to this step is going to change slightly. Everything else stays the same. Try to work out the equation for delta b and tell me in the chat box, what did you get? I'm going to keep this page open for you to refer to how did we solve the delta m. This is how you would work it out. So you would start off with the same thing. Now this time you're going to take partial derivative with respect to b instead of m. You're going to say error square. Now the only thing over here which is going to change is everything else is constant, and the only thing is which is not constant is b, right? So b is not constant over here, but because everything else is constant, it will become 0, and d by dx of x is 1. So it's going to be left with 2 by n times error, right? So this is what you should get. I'm going to wait over here for a few seconds for those who were not able to complete. If you have any questions, if you got stuck somewhere, let me know. And guys, remember that we are going to go in the opposite direction of what delta m and delta b is, right? Because this tangent, we got the slope of this line, which is delta m and delta b. But if this is positive slope, we need to go backwards. We need to go down, right? So we are going to go in the opposite direction of delta m and delta b. So let's say if we got delta m as +1. So we are going to, instead of saying m +1, we're going to say m -1, right? So guys, let's get back to coding. For those who are done deriving delta b, that was the only thing left over there for us, right? We just had to derive delta m and delta b. Now you have the equations for delta m and delta b. Can you guys plug those values in and tell me what do you get? And remember, you have to go in the opposite direction of what delta m and delta b, what you have derived actually, right? So over here, the delta m which we are using is actually negative of what we have derived. So plug those formulas in and tell me what you get, and tell me what's the formula that you are using. Okay, give me paste the line of Python, the 2 lines from your Python code on the chat box. And oh, by the way, let me tell you, in this equation that we derived, okay, so forget about this n over here. Okay, it's anyway a constant, right? This 2 by n over here is a constant, and as you are going to see next time, or no, in next few seconds, we are going to multiply this with something else as well. So forget about that constant. Just focus on this error times x and this error, just the error over here, right? Forget about this n. Don't worry too much about the n over here. It's a constant, right? Even if you adjust it by a constant factor, it's not going to make much difference because of one small thing that we're going to do next. So don't worry about this n. Just tell me these line if you, in case you just go blind on that n for now. So let me just go ahead and put what we have derived. Okay, so we know that we are going to go in the opposite direction. So I'm going to say -1 times, right? Does that make sense? We're going to go in the opposite direction of what we know in the formula over there. Okay, once we know that we are going to go in the opposite direction, the second thing that we got over there is delta m is, and I said forget about the constants over there because we are going to take care of that thing slightly in the next step. I'm going to say that this is error times x, as simple as that, and this is just error over here, right? So no rocket science in that. Save this, and you might say, oh, where did all these constants go? Once again, please stick with me over there. We'll come to that. But this is the direction essentially, right? So once you know that delta m is error times x, delta b is just error. Now let's try to show this again and see what happens. Okay, control S, let's do control B. And can someone tell me what's happening over here? Does this look even correct, or what's going wrong? So it seems like our line over here is going from a small value to a large value over there. Is like something like 1, I guess it's no, it's going to a huge value over there, right? So you see over here the y is something 7.8 times like e raised to 32, right? So something is really wrong over there, right? So what we are actually doing over here is this gradient over here, which we just saw. That's why it's called gradient descent. Now we were taking the gradient of this function with respect to m and b, right? This gradient at this point is gonna give us only the direction, but how far that do we need to move, we don't know that yet. Okay, so we want to move slowly on this curve towards the bottom over here, right? We need to move slowly towards the bottom, and this tangent is only giving us a direction. But can someone tell me what the slope of this line is going to be if this curve is too steep? If you are too much high on this curve over here, it is going to be almost a straight line, right? And what the slope of that straight line is going to be? If we are too high on this curve, right, the value of this tangent, the value of this delta m is going to be you're going to make a straight line. And what's the slope of a straight line? A straight line as in a line which is parallel to y-axis over here, right? Imagine this line was straight, now this y-axis. So what's the slope of this straight line which is parallel to y-axis? It's infinite slope, right? It's very steep, it's infinity. So you are adding delta m, which will tend to infinity if you're too high on the slope, right? Which is not what you want. So what you need to do is take only the direction from this derivative that you took, and the amount of the magnitude by which you should move on this graph, you can take an arbitrarily small number. Rather than moving delta m times, let's just move a little every time. Okay, this delta m is going to give us the direction to which we're going to move, and we need to take the magnitude as a small number. Let's multiply this delta m with a small number, something like 0.05. Okay? You can take different numbers and try it out, do some trial and error, because that's the whole point. But let's try it out with 0.05. I'm multiplying this with a small number because every time we want to move a little bit, we don't want to move infinite amount of times if if we are too high on that curve, right? So I'm multiplying it with 0.05, and that's the reason why I ignored all the other constants as well, right? So let's say if you had 2 by n over there, well, 2 by n multiplied by 0.05 as well, again, you'll end up with a small number there, right? It's not significant enough that you consider all of those things. Let's just get the direction from error times x, and the magnitude by which we need to move, we are gonna say define a small number over there. And this small number is also called as what we call the learning rate of that algorithm, that gradient descent algorithm. This is the learning rate. Okay, so let's try it out with 0.05 and see what we get. Save it. Let's run it. And voila, right? You got something that was close to what we were expecting, right? We are getting a line which seems to be getting there, right? It's not a perfect fit, but much better than what we had before, right? At least it's not going until infinity, right? So, with one gradient descent, with one step of that algorithm, we were able to get this line, which we were able to get m and b, which resulted in this line, right? So what you could do is also, what we can also do is just say print m and b over here. Okay, so this will help us see what the value of m and b did we get. Okay, I'm missing a comma over here. This tells me that it's too late in the evening now. Okay, so what we are saying is we started off with m as 0, 0, m and b as 0, 0. And we have figured out using one step of our gradient descent algorithm, as m is now 11 for us and b is 3. The slope of this line is 11 and the y-intercept is somewhere around 3.46, right? So that's what our graph is telling us, right? So all good until here, right? But how do we improve this, right? So it's still not a perfect fit. We still need to, so what we have done over here is we were somewhere on this curve. Okay, we were on this random point on this curve over here. And we applied gradient descent to arrive at a better point on this curve over here. Okay, so we are somewhere over here now. There is some error, but definitely less than what we had before, right? So how do we go one more step? Well, what we could do is apply the same algorithm multiple times. If we do the same thing multiple times, we will eventually should be arriving at this minima, right? So let's try to do this multiple times. So what we are going to do is, so this is how you would go about writing this. From taking one step of this algorithm, we got a line which was really much better than what starting off a random point, right? Now what we need to do is just apply this thing multiple times. So the basic thing that you could do is, something really simple. We're just gonna write a loop over here. So we're gonna say for I in range, let's say 0 to 10, and I'm gonna say this. Let's just put it inside the loop. I'm gonna say print and plot, as simple as that. I'm gonna apply the same gradient descent algorithm, and remember our gradient descent returns m and b, right? So these m and b's are gonna be the next time when the loop comes in, it is gonna feed the updated values, right? So that's a good thing that we have done. And yeah, we're gonna plot the regression line every time as well. So save this and let's run this. And let's see what happens. And something is happening there, right? Our line is getting better, which is what we would expect. It's not that good, right? But it is trying to get to the point which has the minimum error, right? So with this values of the learning rate, and again, the point to note over here is depending on where you start on this graph, let's say you start over here or no, at which point you start on this graph, you might end up at different minimas, okay? Because this is a function of error, this is, you are seeing it in a 2D plane, but the error in turn depends on M and B, right? So actually when you see it, you might see some other plots, they would show it as a ball or a 3D plane, and on that plane, depending on where you start, you might end up at different answers. So there is no right answer to this. And again, depending on the learning rate that you choose, you might even not converge, you might actually diverge. So here's an example which if I could show you. So depending on the learning rate, this was our gradient, and we are trying to apply this multiple times, right? So first we got over here, we're trying to get to this minima over here, and this is the initial M and B that we started with, right? And depending on the learning rate that you choose, right, over here, if you choose a very large learning rate, you might, instead of going down, you might end up diverging, and you might just end up not converging it in the what you would expect. So no, there is no guarantee that the algorithm that we have written over there would work for any set of data for any set of points, right? um, Choosing that learning rate, you will have to look at the data and try to figure those things out. uh, and again, there are other complicated algorithms as well which will dynamically adjust for that learning rate depending on that data, but that's a topic for some other time. But you should know that depending on the weights that you choose and depending on the learning rate that you choose, your answer is going to differ. So let's try to see if we are learning at a very fast pace right now, which is 0.05. Again, it looks like a small number, but in terms of learning rate, it's not. So let's see if you happen to use 0.0005. Okay. And so in this case, you are going to learn slowly, but you're going to reach to a better answer, right? So this time in the first iteration, we were not that close, but again, towards the 10th iteration, you could see that we are getting there, right? So we are getting to our best possible guess over there. So two questions over there. Why are we multiplying by -1? Let's say we are at this point on this graph. What is the slope of this point? Is the slope of this point going to be positive or negative? Positive. So the idea is go in the opposite direction of what that delta m is. And that's why we multiplied it by -1. Does that make sense now? If we change the delta m and delta b, isn't it possible that the line might move away from other points? What we are trying to do is adjust m and b such that the total error is minimum. So it might not be the best option for that one point, but globally, it would be a better option to adjust that line. So Suchit, yes, gradient descent can work with classification algorithms as well. Looks good and something that you should be proud of doing today evening. I hope you guys had a good time and you enjoyed this session on gradient descent as much as I did. I surely did. But thanks again for coming, and I hope that the next time that you come, you get your friends as well. Tell about us to everyone in your class or in your office. If you had a good experience, definitely. If you didn't have a good experience, tell me and I'll try to improve our future sessions. Okay.